I have an example here of spherical coordinates, and we're going to, part A, convert 0, -4, 3 from Cartesian to spherical coordinates. Part B, we're going to transform the vector field given by this guy. It's got an x component, it's got a z component, to spherical coordinates. And then C, we're going to evaluate the vector field at the point, and we're going to do that in the spherical system. All right, so let's begin with part A. Now let's recall that the radius vector, or the radius of this thing, not vector, excuse me, the radius of this thing is the square root of the sum of the squares. So 0 squared plus -4 squared plus 3 squared. Right, so we've got 16 and we've got 9, so that's 25. So take the square root of that. That's nice, we get 5 there. Okay, so that's one coordinate, and then we need theta, and theta is the inverse tangent of the square root of x squared plus y squared. So that's 0 squared plus -4 squared divided by z. Z is 3. Okay, so that's inverse tangent of 4/3. Inverse tangent of 4/3. So we punch that in and we get 53.1 degrees rounded to 3 significant digits. And you need to be careful about the inverse tangent. Inverse tangent is positive in quadrants 1 and 3. So here we have a positive x and a positive, or two positive numbers. They're a ratio of two positive numbers, so that's quadrant 1, 53.1 degrees. And then finally we're going to get phi, and phi is the inverse tangent of y over x. So that's -4 over 0. -4 over 0. So if we think, what is the coordinate when we have a, or what is the angle when we have a negative y and a 0x? So think about the xy coordinate system, 0x, so 0 left and right, and then go 4 down. That puts us at 270 degrees exactly. Okay, so don't get thrown off by this division by 0. The inverse tangent is well defined there when we divide by 0 there. So our point, that we're calling t, is 5, comma 53.1, and that's rounded, comma 270 degrees. So that's our point there. Okay, so that's part A. All right, let's look at B. So B, we're going to transform that vector field to spherical coordinates, and so I'm gonna lean on the transformation matrix. So that's QR, Q theta, Q phi is equal to, and so this is something that you would want easy access to in your notes, or bookmark it in your textbook or whatever. You don't have to memorize the sine of theta, cosine phi, sine of theta, sine of phi, cosine theta is the first row, right? Second row is cosine theta, cosine phi, I think, and then cosine theta, sine phi, and then negative sine theta. And then we've got negative sine phi, cosine phi, 0. And then what are we going to transform? We're going to transform this is the x component and this is the z component. And before we start putting things in here, I want to point out, you see these square roots of things squared. So this transforms really nicely. First of all, notice that the square root of x squared plus y squared, well, remember that well, let's check it out. So we've got the square root of x squared plus y squared first. So remember that x is r sine theta cosine phi. Remember that? So we've got r squared sine squared theta cosine squared phi. Again, x is r sine theta cosine phi. So that's x squared. And then y is r sine theta sine phi. So when we square that, we've got r squared sine squared theta sine squared phi, right? And so we can pull out actually what's common here is r squared sine squared theta, and then we have left sine squared phi cosine squared plus cosine squared phi, which is 1. So then, so times 1. So we've got r squared sine squared theta, and so the square root of that is just r sine theta. Feel free to stop the video or pause the video, convince yourself that that's equal to r sine theta. We're using the property that sine squared plus cosine squared is equal to 1. So that's really nice, right? The square root of x squared plus y squared is just r sine theta. And so also the square root of x squared plus y squared plus z squared, well, remember that is exactly r, right? That was the radius of this thing. So this is r. I'm not even going to write it down. That's r. So now we're ready to transform, and our x component, now in the numerator we have r sine theta, and in the denominator is r. So r sine theta divided by r is just sine theta. And then there's no y component here, so let's just put a 0 there. And then the z component, we've got y, okay? And we've already said that y is r sine theta sine phi. I'm going to just write that down to remind you. Hopefully this looks familiar. R sine theta sine phi, right? We used it here when we squared y. Okay, so that's y, and then in the denominator is r, so the r's cancel, and we're left with sine theta sine phi, right? So this is what we're transforming. So we do that multiplication, and we see, the transformation that QR is row times column, row 1 times the column. So we get sine squared theta cosine phi, and then 0 of that component, and then we have sine theta cosine theta sine phi, right? And then we do the same thing, we perform the transformation, we get the component in the theta direction, that's this guy, second row times the column. So this is sine theta cosine phi, and then a 0 component, and then we have minus sine squared theta sine phi is the theta component, and then the phi component, that's row 3 times the column. So we've got minus sine theta sine phi, right, and then 0 and then 0. So that's it. So let's be precise here. The vector field now, Q, is, and it's going to be this long guy, but that's okay. We've got I'm just basically copying it again. Sine squared theta cosine phi plus sine theta cosine theta sine phi in the r direction plus sine theta cosine phi minus sine squared theta, we could pull a sine theta out if we wanted to, times sine phi, that's in the theta direction, so times that unit vector in the theta direction, and then we have minus sine theta sine phi in the phi direction, so times that unit vector in the phi direction, and that's the answer. So that's the answer to part B. That's our vectorized, or our spherical coordinates in the vector field there. All right, so C, now we're going to evaluate Q. So evaluate the vector field that we just got at point T. So here's point T. We've got it in spherical coordinates. So this was R, this was theta, and this was phi. Now, let me remind you that theta was rounded to 3 significant digits, and phi was exactly 270, but that was just this problem. Sometimes we round phi as well. So we're going to try to get the exact value here. We don't want the rounding to propagate through to part C. So You know, we've done this a few times. If you're reading or if you're watching the other examples, we've done this a few times. So we're going to do it again here, where we make a triangle, right? So let me just create some space, right? And I'll draw the triangle over here to the left. So what we're saying is that I guess this one doesn't even require a triangle. Phi, right, right here. If I take the tangent of both sides, this is the tangent of phi is equal to negative 4 over 0. So the tangent is the the y over the x. So this means that we're going down 4 and over 0. So think about here's x, here's y. So we're over here somewhere. So what is the what's the so here's the angle, right? 270, right? So what is the cosine? Cosine is the x coordinate. So the cosine of phi, right? This is phi. Cosine of phi is equal to, what do you think? 0, right? That's the x coordinate. And sine of phi is the y coordinate. The y coordinate at that angle, the y coordinate is negative 1, right? Okay, so we can plug those into our vector field down here. So we've got cosine phi, sine phi, but we also need the thetas. So we consult this over here, right above, right? So this was the thing that was rounded, so we don't want that rounding to propagate through. So if I take the tangent of both sides there, so I guess I'm not even going to draw the triangle, tangent of theta is equal to 4 over 3. Yeah, let me draw the triangle. Okay, so here's theta, right? So this is tangent is opposite over adjacent. So opposite has to be 4, adjacent is 3. So that makes this hypotenuse 5, right? And so we can see that from this 3, 4, 5 triangle that the sine of theta is opposite over hypotenuse. So opposite is 4 over hypotenuse 4/5, and the cosine of theta is equal to 3/5 adjacent over hypotenuse. Okay, so now you plug these things all in here. So you plug these guys all into this. Right? You don't just plug the rounded 53.1 in for theta. You plug cosine theta is exactly 3/5. So let me show you what I mean. So we're gonna say Q is equal to, okay, sine squared theta. Well, sine of theta is 4/5. So sine squared of theta is 16 over 25. But then we multiply by cosine phi. Cosine phi is 0. Okay, so I shouldn't have even written that, right? Cosine phi is 0, so this component is 0 here. Now we've got sine theta is 4/5. Cosine theta, okay, is 3/5. Sine phi, okay, so this is non-zero. So we've got 4/5 times 3/5 times minus 1. So that's minus 12 over 25. And then that's the radial component there, plus, okay, now this guy, sine theta is 4/5, cosine theta is 3/5, cosine phi is 0, so this thing is 0, minus sine squared, so sine squared of theta is 4/5 squared, sine phi is minus 1, so that minus 1 makes a positive, and then we have 4/5 squared, so we have 16 over 25, and that is the theta component, like that. And then finally we've got this sine theta, which is 4/5, minus 4/5, and then sine phi is minus 1, so that makes a positive, positive 4/5 times a phi. And that's the answer. You see that? That's the exact answer. No rounding.